This is video 262, and the goal here is to find horizontal and slant asymptotes in order to graph rational functions. So in class we talked about horizontal asymptotes. So remember, horizontal asymptotes are really looking for what happens as x shoots off to infinity. Okay, what happens to the graph? And that's what we're looking for when we're looking for horizontal asymptotes, because we're looking for if there's a boundary, if there's a point at which y can't get any bigger when x gets large, okay? Or maybe y can't get any smaller when x gets large. So remember, the rules are the following, that it's all about the degree, okay? And the degree of the numerator versus the degree of the denominator. So we're looking at the degree, and when the numerator is smaller than the denominator, then the line y equals 0 is our horizontal asymptote. If the two degrees are equal, so remember that means that you'd have something like x squared over x squared minus 5. The two degrees are identical, they're both 2. Then the ratio between the coefficients is going to be your horizontal asymptote. So they're getting these coefficients from their general form of a rational function. In our case, our coefficients are both 1. 1x squared over 1x squared minus 5. So our horizontal asymptote would be 1 when y equals 1. So we have that boundary. This graph will never get bigger than 1, or maybe it'll never get smaller than 1. We have to see it to decide. Is it a little bit bigger than 1, or is it a little bit smaller than 1 always? And what happens as we grow and we get closer and closer to infinity. The final case is when the numerator is larger than the denominator. In this case, there will be no horizontal asymptote. However, there may be a slant asymptote. So we have no horizontal asymptote. There's no boundary, because this means that the numerator will get really large, but the denominator won't be able to keep up. Okay, so the denominator can't keep up with the numerator, so it's going to go off into infinity, maybe negative infinity. But it will not have a boundary that it can't cross when it goes into those large numbers. So the three examples we looked at, here are the graphs of those examples. So the first one, remember the the numerator is smaller than denominator, so that means 0 is my asymptote. So we want to rethink our understanding of asymptote. Asymptote is what happens as we go to infinity or even negative infinity. And we see that the graph shoots off and gets close to 0, but will never equal 0 in the infinity or negative infinity. It'll just get really close to 0. Now the second one, was when the 2 degrees were equal. So now we divide the coefficients. So in this case, 4 divided by 2, we see this boundary line at 2 because that's 4 divided by 2. So this function will never equal 2, and in fact it'll always be less than 2 because it looks like the denominator will always be a little bit bigger than half as much as the numerator because it's 2x squared plus 1. The final one is 4 is to the third versus the second, and this is the one where we have no horizontal asymptote. So we see things shooting off into infinity and negative infinity. But what we also notice is this looks pretty linear, and it seems to follow a pretty straight line. It's not an exactly straight line, but it seems pretty close. This one actually has a slant asymptote, and we'll see why with the next definition. Okay, so this is not having a horizontal because the numerator has a higher degree than the denominator. Let's take a look at slant asymptotes. There will be a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So that's the case we just saw. 4x to the third over 2x squared plus 1. That was our function. The degree here was 1 more than the degree in the denominator. It has to be exactly 1 more than. In this case, we had a slant asymptote, and the simple thing we have to do to find this is to divide the polynomials. So we're going to take 4x to the third, divide it by 2x squared plus 1, and the answer, without the remainder, is the slant asymptote. And what's cool is in calculus, you'll get to prove why. You'll get to see why is it that we don't worry about the remainder. And that is essentially because it's a fraction. And we know denominators of fractions, as they get really large, those things turn into 0. So that remainder will have less impact when we get closer and closer to infinity. So we divide the polynomials, and we're going to do that here. So let's take a look at these two polynomials. We're going to take 4x to the third, and we're going to divide it by 2x squared plus 1. So it looks like it goes into 4x to the third 2x times. Now I could be using a generic rectangle right now. And if I did that, I'd have to write this as a vertical 2x squared plus 1. So 2x times 2x squared is 4x to the third, but then I also have to multiply here. But if I look, I've already got the numerator that I want inside. And my remainder is that 2x, that stuff I don't want. So my result after dividing is this equals 2x plus some remainder r. Who cares? It doesn't matter. The slant asymptote will be 2x. That will be my slant asymptote. So the line y equals 2x is the slant asymptote for this particular function. Let's take a look back at that graph to prove it to ourselves and to make sure we believe it. Y equals 2x. If I graph y equals 2x, I have the line 0, up 1 over 2, up 2 over 1. I keep doing it. And it looks like it's this red line here. But down here, it's kind of below it. But do we see that blue line, the original line, going the same direction of the red? Why, yes, we do. That appears to be the correct slant asymptote. And apparently, this graph will get closer and closer to that. It's not going in a straight line, but it appears to be going in a semi-straight line, almost straight line. So that's how we're going to find slant asymptotes. Let's try one more. So let's try finding the slant asymptote here. So we're going to divide the function, x squared minus 4x minus 5 by x minus 3. And it looks like this has to be x, so negative 3x. And then I want negative 4x, so minus 1x. So that means that this will have to be a negative 1. And then I get 3. So finishing this out properly, my remainder is negative 8. But that's irrelevant. The division answer is the extra factor here, x minus 1. That's the answer with a remainder of negative 8. So this can be rewritten, remember, as x minus 1 plus a remainder of negative 8 over the divisor, x minus 3. Excuse me. This is an equivalent statement because we just divided and wrote the remainder as a fraction. These two are equal. But once again, remember, this is just not going to have an impact. It's all about this. This is my slant asymptote. Y equals x minus 1. So if I were to graph this graph, I would start by graphing the line y equals x minus 1. And that would be one of the boundary lines. Now remember, you can cross an asymptote, but what we're saying is when it goes off to infinity, it's going to get extremely close to this line and practically mirror it, going parallel and getting closer and closer as x gets bigger. So let's take a moment and try to graph this. Let's look at the steps to graphing, and then we're going to graph this function. So the steps to graphing that you want to keep in mind are you want to always find the intercepts. You want to find the vertical asymptotes and the horizontal or slant asymptotes, if there are any. And then you plant a bunch of points. Really, you just have to plot a bunch, plug in some points, figure out what they are. So we've already found the slant asymptote for the first example here. Y equals x minus 1. We know there's no horizontal because from the previous instructions we see that you can't have a horizontal and a slant asymptote at the same time. It's either one or the other, or it's neither. So our next step is, let's take a look at these different values here. Let's find some intercepts and some vertical asymptotes. So I'm going to take a look at this function and remember my previous steps. Okay, x-intercepts occur when the function is 0. Y-intercepts occur when we plug in 0. Okay, so let's plug in 0 and see what we get. If we plug in 0, we're going to get negative 5 over negative 3, or 1.6 repeating. So we have a y-intercept of 1.6 repeating. Okay? That's the first intercept. Now we're going to take a look at the x-intercepts. X-intercepts occur when the function is 0. Taking a look at this function, I'm wondering when it's 0. It will never be 0 if the bottom's 0. Remember, the bottom being 0 will create an asymptote, and it's going to be a vertical. So why don't we record that now? X cannot equal 3, so that will be an asymptote. It may, in fact, be a whole. Remember, the only way to decide if it's a whole is if I factor the numerator. So I'm going to factor the numerator to see, hey, is there going to be a whole here? And if so, I want to write that down. So let's see, the numerator factors into x minus 5 times x plus 1. Okay, I know that just because I'm quick with quadratics. If you're not, you try some things. The only logical things to try, because of the final term, is 5, negative 5, 1, negative 1. And then, of course, we still have my denominator. This reassures me that the vertical asymptote will be at 3. It would be a whole if, in fact, I had the same exact factor on top. But since these factors are different than the denominator, they are not going to be wholes. Now I ask the question, when is this 0? So remember, I don't want to look at the denominator being 0. I want to look at the numerator, because 0 divided by some number, like 5, will be 0. Okay, so when is the numerator 0? So it looks like my two x-intercepts are at 5 and negative 1. Okay, so I have 3 key points already. I have an asymptote and I have another asymptote. So I'm going to sketch this, see where I'm at, and then decide what to do from there. So let's see, I have a asymptote at x equals 3. 1, 2, 3. So this is my first asymptote, my boundary, x equals 3. I also have a slant asymptote at x minus 1. So I'm going to graph x minus 1 down here. And I'm going to graph that line. Using what I know about slope. Make a nice sketch. So there's my slant asymptote. Now remember, these things can be crossing the asymptotes. The key thing is here is what's happening as x gets to infinity and negative infinity. So we're really worried about what happens when we get extremely small. What happens as we get extremely large? And apparently this graph will border these two asymptotes. Okay, so let's take a look at plotting our points and starting to picture what this is going to look like. We have the two intercepts at 5 and negative 1. So here's 5 over here. Here's 5, and then we have another one at negative 1. And then we have a y-intercept at 1.6. Okay, so I'm starting to see my graph, and I'm starting to get ready to sketch my picture. So it looks like I'm starting to see a function that is going to look something like this. And maybe something like this. I'm not quite sure though. Well, that doesn't make sense because then it would be a function. So maybe it's more like that. So it's really hard to tell right now, right? So we're going to plug in some more points and we're going to see what happens with the different functions here. So in order to see the best sketch, I'm going to plug in some numbers. I'm going to plug in negative 2. So I can see what's happening to the left of this red point that I had already. Maybe I'll plug in 1. So I can see what's going to happen at 1 here. Okay, I could plug in 2, see if there's anything interesting happening at 2. And I can also plug in some other values that are positive, like 4 and maybe even 6. Okay, number one way to do this is probably to graph it in your calculator. Okay, that's what I've done in order to get a nice table, and then I can see the different values pretty quick. This is negative 1.4. This is 0. I'm sorry, not 0. This is 4 f of 2.